Hello again, welcome back. So in the previous lecture, we introduced the concept of spin, and we went through a long introduction to ultimately come to the conclusion that the spin is a fundamental property of quantum mechanical particles, where particles can be both truly elementary particles, which means objects which, as of today, can be considered point-like as far as all possible experimental uh, resolution has been achieved. And composite particles, which are particles that have been demonstrated to be made by inner components, more fundamental components. But if observed at a very low resolution, can appear as point-like. Now, such point particles are associated with an intrinsic property, which is called spin, which historically is interpreted classically as the particle is somewhat rotating, but we went through the fact that this idea of rotation is only vaguely related to what the spin really is, and there is no real classical analog of the spin. We just have to assume there is such a thing as a spin and live with it somehow. And in particular, we came to the conclusions that spin is a form of orbital angular momentum. Is a form of angular momentum. And to be more precise, spin is associated to a vector operator, let's call it S, which therefore is a triplet of operator Sx, Sy, and Sc, and that these operators obey commutation relationships, which are the same commutation relationship of the orbital angular momentum. So that's why we say the spin, this is one of the reasons why we believe the spin is in fact a form of angular momentum. This is called the Pauli algebra, and the set of commutation relationship that defines an operator is called an algebra. I'm not going to go into those mathematical aspects in this lecture. So that's why C is equal to Cx and so forth. And we also discover that we have a commutation relationship, which, for each component of the angular momentum commutes, in fact, with the square of the orbital angle. Based on these facts, we can, classify. So this was the analogy with the orbital angular momentum, same commutation relationships. But there are also fundamental differences between the orbital angular momentum and the spin angular momentum. And in terms of this, can only have integer. So if I can construct my spin triplets of operator and deduce, say, these two maximally commuting set of operator L square and Lz, then the orbital angular momentum has only integer eigenvalues. L equals 0, 1, 2, and consequently, for each of them, M will take maximum, will take values from minus L to L in integer steps. But for the spin angular momentum, which will denote it as S, through which we can construct Sz and S squared. Well, S squared can have half integer eigenvalue. So to be more mathematically precise, I can, since S square and SZ commute, I can find a basis that is labeled by the eigenvalues of this operator and the eigenvalues of this. And they are the same states because they are the same joint basis between these two Hermitian operators. And therefore, when I apply S squared to S, Z, I get H bar S, S by 1, S, S, Z, S, S, Z. And when I apply this operator, I get H bar S, C, S, and C. And while this number here is only integer for orbital angular momentum, it can be also a half integer when it comes to spin. And this distinction between integer and half integer, which can all be realized, led to defining two kinds of particles: the fermions and the bosons. Examples of fermions are the electrons, the proton, the neutrons. Example of bosons are the photons, the famous Higgs boson that people might have heard from news recently, finally found at CERN, and so on. Now, the reason it is important to distinguish between integer and half integer to the point to give them different names, it is obviously not clear at this level. It will become clear at the end of this lecture. The behavior of integer and a half integer particle, spin particle, is so different that it makes sense to consider really two families of particles altogether with entirely different properties. And it probably will form the largest dramatic, the most dramatic distinction between particles in physics. But this is subject for today's class. I'm still reviewing what we did in last class. What we did in last class, indeed, was to focus on spin 1/2 particles, so S equal 1/2. And again, this can be the electron, proton, the neutron. Well, there are many more, the positron, the neutrinos, but these are less known to, say, chemical. These are not relevant for chemistry, so I will not discuss them here. I will not discuss them in this lecture. So we are interested in spin 1/2 particle. And in looking at spin 1/2 particle, we realized that, you know, if a particle has spin 1/2, then basically this is 1/2, remember, and I can fix it. And this can be basically only two states, plus 1/2 H bar if you want. So I can forget about the H bar and only write a C. So this is going to be plus 1/2. And this is 1/2 minus 1/2. So as long as I'm interested in, as long as it's implicit that the spin of a particle, that the particle is spin 1/2, in particular when we will be dealing with electrons, we know that the electron has spin 1/2, so we will never bother writing these first quantum numbers when it comes to electrons because it's everybody knows and it's not going to change. So it's just useless consumption of ink to keep on writing this first label. So normally it's quite customary to use this notation in the literature to represent these two states. Now, These are abstract states in the Hilbert space of this quantum spin states of a particle. And if the particle is an electron confined in an atom, where you suppose that you're not interested in where the electron can go because maybe it's confined to a particular location and that's all you care about, then the wave function of the electron will be entirely determined by its spin states. On the other hand, if the particle is allowed to move, then of course you need to specify also the position or the momentum space. So let's for a moment focus, still recapitulating on the previous lecture, on the situation where we are only interested in the spin degrees of freedom of a particle. Then we have a two-dimensional space. So in this particular case, the Hilbert space is actually two-dimensional and not infinite dimensional. So we use a simple vector space representation. And in this vector space representation, basically, the spin up is associated with one of the vectors of spin 1/2, for instance, of the two-dimensional vector space, for instance, 1, 0. And this state is associated with this state. And Pauli and spin matrices are associated, spin operators are associated with matrices. Of course, the matrices must be Hermitian because the spin is observable. And these matrices here, which are proportional to the spin operator representation, are the so-called Pauli matrices. There are obviously three Pauli matrices. They're usually denoted as tau, tau x, tau y, tau z, proportional to the spin operator in the mathematical representation of spin. So, for instance, let's see if we can understand the fundamental properties of, let's go back to the analysis of the Stern Gerlach experiments based on just whatever we know, whatever we have done so far about spin. We have a beam of spin electrons, for instance. And let's suppose for simplicity that all these electrons are, are produced in a reaction and they have basically all the same momentum, P. So we fixed, obviously, the nice and simple way of representing this quantum state would be, of the electrons, would be through their momentum and through their spin components. So this means that in general, if all these states have the same momentum, there would be a certain probability for the electrons to have spin up, and a certain probability, let's call it alpha down, for the electrons to have spin down. And these two components are normally called the spinors, which means that basically when you project the state of a system into momentum space, you get a wave function of P. And when you project on a different state, you get a different wave functions. And so if you combine these two objects into a vector, you call this a two-dimensional spinor. This is a spinor representation of the electron wave function. Now we have a spinor representation of the electron wave function. That sounds good enough. But now, even without, so we can sort of, if we assume that all the particles are the same momentum space like we did here, we don't even have to specify the momentum because it's the same for all particles. So all we really care is really the spin quantum state, spin degrees of freedom. And now, after we measure, so basically the probability of splitting will be proportional to the different components of the wave function. So in particular, if my initial state is completely democratic, so we'll have equal probability of being up and down, then I can take this to be 1 over root of 2 and 1 over root of 2. In fact, the probability of observing spin-off would be up psi modulo square, and take you some time to realize that this is 1/2, and the probability of observing spin down will be again down psi square, and this is going to be still 1/2. Now I perform a measurement of the x orbital angular momentum, right? Here. So what I can now, what does it mean? I mean that I must compute. So the average, the possible outcome of the measurement of the x angular momentum are the eigenstates of the xx components. So what are the eigenstates of the x spiny matrix? Well, to find out, I have to compute the secular determinant. I'm gonna get determinant of h bar half negative lambda 1 1 negative lambda equals 0, which means basically lambda squared minus 1 and therefore this can be plus and minus 1, and therefore once again the possible outcome of measurement of the excess component is going to be plus h bar half or negative h bar half. So that's why when we perform the Stern Gerlach we have this democratic measurement. So what are these eigenstates in this representation? They are the corresponding eigenvalues. So let's compute. I take what are the eigenvalues of xs. I have two components, vectors, so I have to fix two variables. The first component, how do I find the eigenvalue? Simply solve this equation. So this is going to be h bar half xy. And if you look at, well, this is simply the equation xc of my sx must be f sx, right? And I'm translating this into equations, and this will be 0 times x. And then, if you in the end do the calculation, you discover that the eigenvalues of xx are related to basically 1 over root of 2, 1, 1. Let's figure out. Let's make sure that this is actually true. Well, we can forget about this. If I do 1, 1, let's see what I get here. For simplicity, I only focus on this part. 0 to 1, I get 1. 0 to 1, I get 1. And then you can go on and discover the probability of finding the converse, meaning opposite spin x state is in fact hold on, it's just taking a long time to work. And the other eigenstates, the one associated to negative 1/2, will be this. It's going to be minus. Okay. So going back to our Stern Gerlach story. In our Stern Gerlach story, we have already measured the z components, and we have found the system had 50% probability to shift between up and down, and then 50% probability to shift the up in right and left. So this is right and left, which means if you want, right is the Sx equal plus 1/2. And now the question we may ask is, what is the probability to observe spin Sz positive or Sz negative if we perform once again the measurement along the z direction? Remember again the Stern Gerlach. So what is the probability of observing plus component of the z angular momentum, knowing that my system is in the one of the two eigenstates of the x, meaning we have prepared a system right here? Well, in order to find out, I have to take the square modulus of plus over these states that I prepared here, the right eigenstates. And if you do the calculation, you'll discover that this is 1/2, and then you have the same probability to find the probability of observing negative. So basically what I'm trying to do, please rewind this part of the lecture and do calculations yourself, is that the mathematical formalism we introduced in the spin is able to completely account in a very detailed way for the Stern Gerlach experiment phenomenology that we started off from. So it does provide a very good representation.